Hello everyone, welcome back to another Eng 130 video tutorial. In this tutorial we're just going to do another angle between two vectors example, except this time it's going to be a little bit more complex because the picture just has a lot more going on in it than the previous example. Alright, so let's begin. Alright, so looking at the question, it's very simple. It just wants us to determine the angle theta between the two cables. So if you guys will recall, there's a special formula that we use when trying to find the angle between two vectors, and it's called the dot product formula. So that formula states that the cosine of theta, and that theta right there, that is the angle between the two vectors that we want. It's going to be equal to our vector 1 dot our vector 2, and this has to be divided, of course, by the magnitude of vector 1 multiplied by the magnitude of vector 2. So real quick before I begin, I just want to reiterate that these don't have to be position vectors. I drew the r as a position vector right now, but of course they could be force vectors or even unit vectors. And again, the unit vectors are really nice because the magnitude of unit vector is 1. So if this was a unit vector, we wouldn't have to worry about the bottom here. It would just be cosine of theta is equal to unit vector 1 dot unit vector 2, which of course is really, really nice. However, when we have an example like this where we have to find the position vector anyways, to take that extra step to find the unit vector may not be worth it. However, in some examples you're given unit vectors or you have to calculate the unit vectors beforehand. So if you already have them handy, it's really great to use. However, in this case we don't have them handy, so it's just easier to use the position vectors, of course. So when we're trying to find the angle between two cables, again, we have to use the two position vectors. That's it. If we're not given anything else, we can start with position vectors. That's easy. So we're going to have two position vectors, R1 and R2. However, in our case, we have R and AC. So RAC, and that's a position vector that goes from this point all the way to C. And we have a second one, which I'll do in blue, and this will be RAB. And this one goes from point A to point B. So remember, all we have to do for this example is really just find those position vectors, and they're really, really simple to find. So I'm going to go RAB first, just because B is before C, I guess. Not very sound logic there, but it works. So if we want position vector RAB, so the position vector that goes from point A to point B, what we're going to do is we're going to take the coordinates at B minus the coordinates at A. So we're taking our final position and subtracting our initial position to find our relative movement between the 2 points. So if we look at B, what we're going to find is we're going to start off with the x, so how far point B is along the x-axis. And even though it's not very clear, B is actually, so hold on, sorry, I'm just going to make this clear. The first point, we're just going to find out how far it goes along this x-axis here. And if you look at B, it actually doesn't go anywhere along the x-axis. It's actually at 0. So the first point is going to be 0, comma. And then the next is we're going to find out how far it goes along the y-axis. So going in this direction, remember, along the positive y-axis. And if we look, it goes a distance of 3 meters. So the second point is going to be 3. And then finally, we want to see how far position B is from the z-axis. So I like to say how vertical it is, even though that may not be the best term. But if we look, it's similar to the x-axis where it actually has no z component. So it's going to be 0 again. And we're going to subtract point A. So we're going to look at point A. And the first thing we want to do is find out how far it is along the x-axis. So this direction here. And if we look at that, it's actually 2 meters along the x-axis. So we're going to have 2, comma. And the next part, how far along it is along the y-axis. And we see it's a distance of 3 meters. However, this 3 meters is going into the negative y direction. So we're going to have minus 3. And then finally, we want to see how vertical it is, or how far along the z-axis it is. So this direction kind of up here. And we see that it's plus 3 meters. So this 3 meters here. So it's going to be equal to 3. Perfect. So now what we can do is we can subtract those components to find out that RAB, so it's a vector, so we're going to have the little hat, and we're going to have the little squiggle components. So the first one we're going to have is 0 minus 2. So this is going to be negative 2, and that's in the I direction. The second one we're going to have 3 minus negative 3. So 3 plus 3, we're going to have plus 6, and that's in the J direction. So the J direction, of course, is the Y direction. And then finally, we're going to have 0 minus 3, so minus 3, and that right there is in the K direction. Perfect. And since this is a unit vector, we have to include the, sorry, this isn't a unit vector. What I'm trying to say is, since this is a position vector, we have to include the units. So the units for these distances are all measured in meters, so this position vector here will have units of meters. Perfect. So I'm just going to erase all the kind of the blue here as we move on to the next one to make things a little bit easier to follow. Because next we're going to do position vector RAC. So we got position vector RAC. It's a vector, so we're going to put the little hat. And this goes from point A to point C. So of course we're going to have the coordinates of C minus the coordinates of A. And if we look at our diagram here, we're going to start with point C. We're going to look up at C, and the first thing we want to see is how far along the X it is going. So we're going to look at this direction here, and we see that it goes 2 meters in the X direction. However, it goes into the negative X direction, so the first point here is going to be negative 2. Second, we want to see how far it goes along the Y direction, so it's simple. It goes 3 meters in the Y direction, so we're going to have 3. And then finally, we want to see how far it goes in the vertical direction, so this Z direction here, and we find out that that is 4 meters, so we're going to have 4. And what's nice is we already found point A above, so we can just put that in. So it's 2, negative 3, and 3. So the real hardest part of this example is just, sorry, finding those coordinate points and making sure you have the right coordinate points. If you mess up one of these coordinate points either by having the wrong number, your answer will be wrong, or if it goes in the negative direction but you account for it as a positive value, it'll also be incorrect. So once we do all the calculations, we're going to find out that RAC is equal to, and we're going to do the squiggle bracket. So the first values can be negative 2 minus 2, so we're going to have negative 4i. Remember, you have to include the I to indicate which direction it is. Then we're going to have 3 minus negative 3, so we're going to go plus 6j, so plus 6, and that's in the j direction. And finally, we're going to go 4 minus 3, so this is going to be plus 1, and that's in the k direction. So we're going to end the squiggle brackets, and of course it has units of meters. So now that we have our two position vectors, we can almost solve for that angle theta. However, if we look at the formula here, we're missing one thing, and those are the magnitudes right there. But again, the magnitudes are one of the more simple parts, so we can do that real quick. So if we're looking for the magnitude of RAB, right there, we know it's just going to be equal to the square root of all the components squared and added together. So we're going to go 2 squared plus 6 squared plus 3 squared. And we're just going to close this bracket here, or not bracket I guess, but the top of the square root sign. I'll try and do it a little bit nicer. Oh, well, it's not getting nicer, sorry guys. And what we find is that the magnitude of RAB is equal to 7. And the magnitude also has units, and that is meters. And again, if we were to look at the diagram here, what that 7 physically represents is the length here of this line is 7 meters long. So the magnitude of position vector is how long, or the distance between 2 points. So similarly, we're going to do this for RAC. So the magnitude of RAC is going to be equal to, and we're going to square root, and then we're going to do all the components squared. So we're going to have 4 squared plus 6 squared plus 1 squared. We do the square root sign. It turned out a little bit better, but still not the best. And what we're going to find out is this is going to be equal to 7.28 meters. So again, if we were to look at this line, the distance of this line is 7.28 meters. So that's what it physically represents. And now if we look at this formula, we have everything we need to solve for our theta there. And instead of doing this all in one big step, what I recommend to you guys is let's just find out this, and let's do this in green. Let's find out this dot product kind of as a separate step. Otherwise it get kind of messy. So I'm going to do RAB dot RAC. And what you guys will find is it doesn't matter if you go RAB dot RAC or if you do it the opposite and we go RAC dot RAB, they'll give you the exact same answer. So what we're going to do is we're just going to have this equal to, and remember the dot product, all we do is we take each term and kind of multiply them together, and then we add up everything at the end. So in order to make this probably as kind of straightforward as possible, I'm just going to write everything out real quick. So we're going to start with RAB, and it's going to be negative 2I plus 6J, and then minus 3K, and that's meters. And we're dotting this to RAC, which we know is negative 4I plus 6J plus 1K. And again, this is also in meters. So the dot product's nice because all we're going to do is take each component and dot them together. So I wrote it kind of like this on purpose, even though you guys probably won't believe me, but it makes it really easy to see, because when we're talking about the components that we're multiplying together, it's going to be the I components. We're going to have these. Oh, that is not what I wanted to do. All right, here, let's try and do this again, a little bit nicer. So these are going to be the first two components. So in the dot product, we're going to have negative 2 multiplied by negative 4. And we're going to add that to the second component. So the second component is going to be the J components. Oh, that worked out not too bad. So this one's going to be 6 times 6. Then we're going to add that to the final components, which are the K components. Actually, I'm just going to erase this because I need to show you guys something. So our last ones are the K components. So the only reason why I erased the Y, because I want to show you guys, is the first value is actually negative 3. You have to be careful and make sure that you have your negatives correctly. And the last component is 1. So this is fairly simple afterwards. Negative 2 times negative 4, we're going to have 8. Plus 6 times 6 is 36. Plus negative 3 times 1 is negative 3. So if we add all those together, what we're going to get here is 41. So a value of 41. Now we can go back to our dot product, our formula up here. And if we start substituting values in, what we have is we're going to have the cosine of theta. And remember, theta is what we want in the end. That's our kind of end all. And it's going to be RAB dot RAC, which we already found out up here is 41. So it's going to be 41. And it's divided by both of the magnitudes multiplied by each other. So the bottom here is going to be 7 and then 7.28. And then we're going to divide them. So what we can do is we can find out this number and then inverse cosine it. And what we're going to find is that our theta here is equal to 36.4 degrees. And that's it. So the last thing that we want to do, of course, is we're going to want to box our answer because it's our final answer. Oh, not box it like that. That does not look too nice. All right, let's see if this works better. Oh, it works perfectly. All right, so that's it. So again, finding the angle between two vectors, it's not that bad. It's usually a case that you do at the very end of a question. So in a midterm, we'll ask you to maybe add some vectors and then do stuff like that. Maybe find a moment. And then at the very end, it'll ask you, oh, by the way, what's the angle between these two vectors? And what's nice is by that time, you'll usually have a unit vector. So you can use this formula as a unit vector, and since the magnitude is 1, all you really have to worry about is that little dot product there. And other than that, the hardest part, I feel, is just finding those coordinate points. Because with those coordinate points, you can easily get the position vectors, and then with the position vectors, you can easily find the magnitudes. And once you have all that, you can just substitute into the formula. I know the dot product there looks kind of scary because well, it's dot. You guys have never seen it before. It's not from high school, so it's a little new. But it's not that bad, as you guys see. We just multiply each component together, and then we add up to get one sum. And then we can just substitute into that formula to find theta. So that's it for this example, guys. Thank you so much. This right now is the last example for week 2. So next week we'll be getting into some new material, and some material I really like because it has, well, in my opinion, more real-world applications, as you guys will see. I'm not sure about you guys, but I know personally myself, I always find concepts easier if I can visually see them to more realistic situations. I don't know if you guys are the same, but that's just how I feel. And then I can tell you guys, I can relate it a little bit more towards the real world. Being a structural engineer, the stuff that we see coming up will actually, you can actually see in the real world, and it's really nice to see. All right, so thank you so much, guys, and I'll see you guys in the next video.